On a week from Saturday on on April 21st at OTC, we're going to do some things with the freshmen to get them oriented into petroleum engineering. We're going to take the group of freshmen, we're going to split them in two groups. In the morning, half of us going to the building. We're going to learn how to make resumes, have interviews, and have industry people help them do that. And then the other half of the group will go to OTC. And out there we're going to have some other industry engineers. We're going to be talking about these things. But we need some supervisors. We divide the freshmen up. We're looking for some senior leadership that would go out there and with the freshmen take a group of 10 or so, take them through these different stations. So like through here, you'd be an engineering supervisor explaining the engineering part of it to them. There'd be other people out there to help explain it. We have a workover unit out there for key energy. So we'll have a lot of things to talk about and do. We've also got a roustabout crew. We have shovels, rakes, hose, pipe wrenches, paintbrushes, just to give them a kind of like about an hour internship. A lot of things. They'll be out there for 3 hours. So we need some people in the morning, we need some people in the afternoon. If you can help with that, I appreciate it. You need help today. See me if you can do that. We need to correct one thing on the field trip. When we went to see Oxy. Okay. Does it work? When we went to see Oxy with our group on Thursday, talking about the separator that was there at the battery and the gun barrel. And they talked about the production went in the gun barrel first and then went over to the separator and then back to the oil tank. And the guy he was a little nervous. He's afraid of public speaking. Everybody's afraid of public speaking, right? It's called your lizard brain. It's a defense mechanism. My wife's a psychologist, and I get it all the time. But people get afraid of public speaking. He was a little hesitant. He got a little confused. But by Friday, he was feeling a lot better, and we got the process straightened out. The production comes from that header to that big free water knockout, the big separator. The oil from that goes to the gun barrel for a final treatment. And then the oil goes to the stock tanks, the water goes back over to the water station, okay? So that was the right process to flow, and everybody hears the right thing now, okay? Okay, don't forget this boot camp. Today we're going to talk about water treating, water injection. I think you saw a lot of that out there at Oxy. It was a good time to take that trip because a lot of what they do is handling water. Water injection, water handling, you need to think of it from cradle to grave. Where do I go with this water that I'm producing out of a well? What's the ultimate disposition of it? What stages do I have to take it through? So we're talking about in our senior design project about water floods. Everybody has water to handle though, whether you're doing it in a water flood or whether you're going to dispose of it. Are you going to recycle it or are you going to use it as is? So we'll consider all of these topics. Water source, talk about compatibility and the volumes that we handle. We're going to look at different sources of water and how they intermix. Gathering systems, it seems like a strange statement, but water runs downhill. You can build entire water gathering systems if you'll put your water station at the lowest spot on the lease. And just let the water naturally flow down to those tanks and alleviate the need for pumps. We have regulations to follow about lease water crossing lease lines. A lot of that is contractual relationships with landowners. Some of it are state laws. And as water gets to be a more scarce commodity and people look at it as a resource, some of those regulations are even being relaxed a little bit. So we need to understand how those fit in the picture. If we go to either an injection plant or a water station, we're going to be doing several things to treat the water, and we're going to need several pieces of equipment, like the gas boot, the filters, the head tanks. We'll go into detail in a lot of this equipment in more detail. The distribution system, the piping we have to consider, the corrosion aspects of it. What are we going to do to protect steel, or are we going to use steel at all? Erosional considerations have to be put into play, and we talked about erosion considerations, but a lot of times we don't think about what's the minimum rate I want going through a line to keep it clean, because if I allow dirt, debris, iron deposits to build up in the bottom of a pipe, that's a great place for corrosion cells to start, bacterial growth. And then there's linings that we can consider as well as non-metallic parts. Going to the wells, and the wells have to be considered part of your facility when you're using an injection well. Cathodic protection, I don't think, how many of you know what cathodic protection is? We don't talk about it much in our production classes, but using a positive charge to keep the electrons from leaving our pipe and causing a corrosion cell. And so we can impress an electrical current on that pipe and create a reverse current where we're not taking iron molecules away from the pipe and creating corrosion from the outside. We have to consider the integrity of the casing tubing annulus. It's not only a best practice, it's a state law in many states, in virtually all states. And then we have surface pressure limitations that we're going to need to work with, and we're going to need to understand frac gradients to do adequate facility design. Water flood plants can be in a lot of places. This is the Wabash River in Indiana, and all the buildings are up on 8-foot stilts, and most of the time you can drive to the water flood plant. The tanks feeding the pumps that are inside this station, this is tank battery equipment. But when the Wabash River floods, the only way you get to the water flood plant is in a boat. And then the water recedes, and the only way you get out there is in a four-wheeler. And then it dries up again, and you're on the ground. So water plant and water flood and takes on some new meanings sometimes. Water quality. What do we mean when we talk about quality of water? We've got to be concerned about a reservoir that, even though the fluids came out of it, we're going to try to be sticking it back in the ground, and that water's got to meet certain specifications. Here's some criteria for quality injection water. Whether it's going in a disposal well or whether it's going in a water injection well for pressure maintenance. It can't contain particles large enough to cause formation damage. And those particles can be solids, they can be oil, or they can be gas. All of those need to be treated as contaminants in water. Quality injection water will not cause corrosion. In other words, the water itself, if we have a lack of oxygen, is harmless. If we left oxygen in there with the water, then we've created a corrosion cell. We want a water that doesn't create a scale or any other precipitate. And a lot of times when we mix waters, we can do that very thing, because there'll be the ion exchanges that will cause a calcium carbonate to form. So if we can keep those ions from ever coming in contact with each other, we can eliminate that precipitation. Good quality water doesn't contain bacteria that can cause corrosion. How many of you ever heard of the Panhandle field up north of Amarillo? It's a gas field. When that field was first discovered, it produced sweet gas and no H2S in it hardly at all. Over the course of time, as they brought in more and more completions, they used water. The water was oxygen saturated. The water contained just enough bacteria that now the West Panhandle field is a sour gas field.
all because of the sulfate-reducing bacteria that were introduced over time in the water that was used for fracks. So water can cause a lot of inadvertent problems that we don't necessarily think of when we first use it. And with all of this criteria on there, it still has to be affordable. What should a barrel of water cost? Or you ever tried to buy a barrel of water? What would this cost by the barrel? This is $1.50 or $2, depending on where you are. If it's $2 and if it's a fourth of a gallon, that's $8 a gallon times $40 a barrel, will be $320 a barrel for this. And we drink it like it's water. So water can become a very precious commodity, and if we are paying those kind of prices in the oil field for our injection systems, we're not going to have very many economic water flows. And there are some ways of treating water, but however we treat the water, it's got to be affordable for the use that we intended. There can be multiple water sources. This map or this diagram illustrates a large company down in the Midland Basin that's putting together a gathering system for water distribution. Notice this starts up here north of Midland, pipelines connecting all the way down into Reagan County. This is almost 100 miles long. And in that system, they're going to be bringing in produced water from tank batteries. They'll be bringing in brackish water. In other words, there's some formations that have some contaminations in it. It's not potable, can't be for human consumption without additional treating. There will also be effluent from Midland and Odessa brought into that line. And this is all designed to bring water together that can be used for fracking and can be used for drilling. And then finally, the system can also take water from USDWs. What's a USDW? U.S. drinking water aquifer. So that's you've heard of the Ogallala, is a freshwater aquifer. Question?
What does the U.S. stand for?
Right. You waited 12 minutes for that. So fresh water can be combined in there too. And this is the thing that causes a lot of this pressure on water, is the drinking water. People understand drinking water. You start messing with this, and when you turn on the tap and it tastes bad, is there an oil well somewhere near that's contaminating my drinking water? People will understand that faster than anything. I served on a task force put together by the Texas Academy of Science, Medicine, and Engineering, Thomas. We had experts in all these different fields of studying the impacts, environmental impacts on shale development. One whole chapter of that was devoted to water. And water is one thing that people understand very quickly. Another one is air pollution. They can see those, taste them, smell them, and those things will really jump out to the forefront. Has anybody ever used a stiff diagram? Have you ever heard of it? Have you taken a fluid mechanics course? Do you have McCain's book? It's in there. And you guys didn't study this, did you? So I've already talked to Dr. Gamati. They're going to study this from him. A stiff diagram is just a way of looking at the ions that are in water. So you'll have your, this is a little hard to read. This is copied right out of McCain's book. Your positive ions on one side, your negative on the other. And so fresh water, no chloride content, looks just like a straight line virtually. Hardly anything in it. Seawater, on the other hand, has high concentrations of chlorides, other salts that are in seawater. And then every oil field water has a unique pattern to it. So those contaminants, those salts, those ions will be unique to the different produced waters that we see. And what we want to do is avoid mixing waters that would create a precipitate. We get a lot of calcium out of this one, a lot of CO, carbon dioxide, carbon monoxide out of another one, and we mix those together and we get calcium carbonate. We're forming a scale. And so we can look at stiff diagrams and pretty quickly tell if we're going to have potential problems. We can also use these by plotting them and look at water flood maintenance. If we're producing water and it has this characteristic to it, and our injection water looks like this, we can take a sample and we can distinguish between produced water and injection water. And so we have ways of using this. This is a really useful tool. This is one way to do it. Your chemical labs will also have lots of measurements and testing that they can do to determine compatibility of waters. You need to test them before you ever mix them together. There's lots of water treating technologies out there because it is popular, because it's being highlighted, that people think, well, let's just recycle the water. Not all produced water can be economically recycled. All produced water can be recycled, but not economically. And so there's a cost to doing everything. One thing you have to remember is that produced water doesn't have to be cleaned up to drinking water standards to be used in the oil field. We can live with a lot of things in the water that we couldn't if we're going to drink it. The other thing that we need to remember too is because the water came out, the produced water came out, it's not necessarily the same as the native formation water. Once we brought that produced water to the surface, it's been contaminated with things like corrosion inhibitor, emulsioner breaker, scale inhibitor, acid, iron. All of those things we've added to the water. So, well, you say it came out, it's at the battery, I can stick it back in. Not necessarily so, because in the process we've changed things. This is a list, and it's fairly, I don't know if it's totally comprehensive, but it's a list of the technologies that can be used to treat produced water. There's all different types and descriptions of these, but they vary wildly in cost. We're not going to try to go through them all and explain them. Here's one that might look kind of familiar: pressure-driven membrane separation technologies. Where do we see membranes? Oxy's plant, yeah. They were separating molecules of different sizes using a membrane. So apply that principle to treating fresh water. One of the most expensive is reverse osmosis. Some of you saw at the Oxy plant, the RO plant that they had for treating water. That's very, very expensive. And the other thing to consider too is even though these processes get the water in good shape, the processes themselves can create other waste streams that have to be handled. If we've knocked out these salts, what do we do with them? There is a plant tied to a brackish water plant in El Paso, Texas, that claims they can take brackish water that they produce from that area down there, they treat it at the plant, and then they turn that treated water straight over to the city of El Paso for distribution in water lines. And every salt they took out of that plant, they have a product they can make. Whether it's wallboard for construction or some fertilizers, everything they took out of that water, they've got an end product they can make out of it and use it. And they're going to try to sell you all of these things when you get out as an engineer. And the guy's going to come in giving you baseball caps and free Cokes. And he'll tell you he's got the latest, greatest way to treat produced water. So you want to make sure you understand it and that you can put some economics to it, that it really will do. It probably really will treat water, but can you afford it? Okay, some of these now on design, system design pressure. Let's look at what we have to consider when we start handling the fluids. First of all, we talk a lot about average conditions. This picture was taken in Maverick County, which is down on the Mexican border, just outside Eagle Pass. And then for those of you that aren't familiar from Texas, this is west of San Antonio. So average temperature, maybe year-round, is about 60 degrees. In the winter of 1983, it froze solid for 2 days. We just laid fresh injection pipe on the ground that wasn't screwed together. It was fitted together. It had like a bell end on it, a male end on it, and then those were put in a machine and jammed together. It went together fast. We could lay it fast. It was steel line. It had a liner in it, good corrosion protection. This winter hit, and you can see what happened at the batteries and around the wells where the pipe burst. But every bit of that Ziploc type pipe that we put together separated at the joints. And so we just had piece after piece after piece of 20, 30-foot joints just laying in the pasture all over the place. But we designed for average conditions. And we didn't take into account the extremes. You need to understand the endpoints. In the old days, we'd worry a lot about what the Aggies were doing. And the Aggies would stand, one guy would have his one foot in a bucket of cold water and the other foot in a bucket of fire. And on the average, he was comfortable. So you need to define your design conditions. Let's look at system design pressure. How would we even have a guess at what we're going to need if we're doing a water flood and what that pressure is going to have to be? We ought to design so that we can at least reach parting pressure in our reservoir with our injection well. We don't want to be injecting above parting pressure generally, because what are we doing then? You're fracking, so we're creating a frac, propagating a frac. A frac goes straight to a producing well, and we water out the well. So we want to go right up to that, but probably never go over it. So if we have a well at 5,000 feet with fracture gradient of 0.65 psi per foot, and we're injecting water that's a little salty at 1.06 specific gravity, we'll look at what pressure we can put on that wellhead, and just for a starting point, let's assume that 10% of our average pump discharge pressure is going to be taken up by piping friction getting to the well. So what pump discharge pressure would we have to design for to get to that well with the pressure right above parting pressure? Well, the frac pressure is just simply going to be the 0.65 gradient times 5,000 feet, 3,250 psi we're going to have on the surface. We've got a hydrostatic head in the well of 5,000 feet times the 1.0 specific gravity times a gradient of 0.434 psi per foot, or 0.433. Our pump discharge pressure then is that maximum that we have to have, 3,250, less whatever we got for hydrostatic, and assuming a 10% for friction, we need 1,045 psi back at the pump. So on my first pass on that pump, I'm going to say I need about 1,050 pounds at my station. And my pump I buy is going to have to design for that. Now you can refine that calculation as you get pipe sized, as you get your specific components in place and take into account actual pressure drops. But that's going to give you a starting point at where you look at it, what you want that maximum station discharge pressure to be. And that's going to become important because you got to buy the pump for that. You have to buy all the tubulars for that as well. And remember, again, back at Oxy, what were they using for their injection lines out to their wells? Fiberglass. They could put water in those fiberglass pipes, and that was running out there. So they're fiberglass. They've got to know what kind of pressure is going to be leaving that station. Let's look at the station itself. And remember, a lot of the things we talk about for a water flood station are going to apply for a water station for disposal as well. Generally, the disposal stations are going to have wells that can take a lot of stuff on a vacuum. They're not going to be putting up much pressure, or as least as possible. They're going to be injecting into a zone that has a lot of permeability, that they can get the pressure away, that they can get the water away at minimal expense. Your water flood, on the other hand, you're going to have to clean it up a little better than that, because you're dealing probably with a little lower perm reservoir. You won't have those kind of conditions to work with. So here's a typical flow path through a water flood station. And let's assume that we're taking produced water. Our flow path would look something like this. We'd go through a gas boot. Remember, looking again, Oxy was a great time for the field crew, because they, right in front of their gun barrel, they had that big pipe with a bigger section on the top. That's what a gas boot is. So we'd separate that final piece of gas out of the produced water before we go into a produced water tank. And we'll look at the innards of a produced water tank here in just a second. That helps remove the gas. It's going to also help separate any last oil that might be carried over in our produced water. And remember, now we're treating oil as a waste product. It's a contaminant to our water. We'll ship it to a skim tank, let it overflow to the skim tank, and then we'll ship it back to the battery for treating. We get good produced water out of the tank. The next thing we're probably going to want to do is filter it down to, say, a 25 micron level. To do that, we've got a couple of filters. And why do I have two? I could probably design one that would handle the flow rate. Why would I want two?
Just in case one gets blocked.
Okay, if one of them plugs up, these are what's generally called rapid rate sand filters. If one of them plugs, if it gets oil on it, I've got to stay in business. I've still got to get rid of my water, and I want my water flood pressure to be held up. I don't want to lose that pressure bank that I've created. So while I'm pumping through one filter to my wells, I can be backwashing the second filter. Anybody ever worked with swimming pool equipment? Yeah. Somebody's making money on it. When you have a swimming pool, you have a filter that you backwash. Maybe it may be a sand filter, it may be diatomaceous earth, but either one of those have to be backwashed. So then once we've got our water filtered, we can go to our head tank. And at this point, this is where we bring in any makeup water. We've got it treated to the point we want it. We can introduce it to the head tank. What do you think a head tank is for? Hydrostatic head. That's exactly it. It doesn't have to be exceptionally large. All its purpose is to build a column of water great enough to give us the net positive suction head we need for whatever type of pump we've got to go to our water flow. So we've got a tank that we'll set in here just for a head tank, and its sole purpose in life is just to feed a pump. We go to our pump, whatever kind that is, and then through our distribution system to our wells. What we probably would have if we had a disposal station, we wouldn't have the filters. This produced water tank, in effect, would become like a big gun barrel. It's going to be a final stage where they separate oil that gets trucked in there with the water. And believe it or not, oil gets trucked in with the water. A lot of these guys with these disposal stations set up the side of the road make a good living on the oil they skim off. So the disposal station would have the produced water tank, a skim tank, they're going to get the oil, and then they're going to go to a head tank and a pump and to wherever their disposal wells are. This is it's a diagram of a wash tank, and it was really designed to treat power oil, where we had subsurface hydraulic systems. And the power oil would go in the tank, just through a gas boot. This power fluid, or you can think water, would come in here, you go into this top section, the gas would be allowed to rise up through here, we're going over to what's now a vapor recovery unit. The water separates and falls down this column of pipe. Gas separates, goes out the top, so that's a small gas separator up on the top. It's also got what's called a tangential entry. In other words, if instead of the pipe coming straight into the side of the gas boot, This one comes over along the tangent here, and then the fluid is introduced this way. Why would we do that? Yeah, we're creating a spinning motion. One of the ways of getting water or getting liquid gas separation is change of direction. So as soon as we're coming in, we're creating that change of direction. We're doing this slow enough so that the gas can go out the top, water can go down, but water goes down slow enough as well where it's not keeping gas from coming out. This would come out. In this case, they have a weir box, and that's just to address fluid levels. So the fluid comes in through the weir box. That's where they adjust their column, and then back into the bottom of the tank. Water would enter. It would be through a series of spreader plates where the water would be spread out over the full diameter of the tank. I want a large diameter in a gun barrel or a water tank to let that fluid rise up and use the maximum diameter of the tank. If I just dump it in and I don't have any baffles, if I don't have these spreader plates, then I've effectively, I might as well just bought a skinny little tank, just made a pipe there for it to go up. Because if I bought that big tank, I've got to get the fluid out to the edges of that tank for it to be effective. Oil can be skimmed off the top, water going over to our next tank. Tanks. Cone bottom tanks make for easier cleaning. What's a cone bottom tank? Yeah, okay, so tank with a cone in it, right? Like ice cream. So it has a taper from the edges towards the middle, and then the tank skirt around those edges. You can't tell it from the exterior, but it looks just like a solid, straight up and down tank. But there's a cone bottom in it where that solids can fall to the middle of the tank. You've got a line in there where you can clean that out. So a cone bottom tank made for easier cleaning, especially if we're going to be using it in our water cleaning applications where we're going to be looking to drop out sand, iron, rust, things like that. Hold gas blankets on tanks to exclude oxygen, corrosion protection. Talked about velocities in that pipe, and I know you've been taught a lot of fluid mechanics on what separation terminal velocities are for gas bubbles, and depending on the micron size. For a rule of thumb, a quick design, that downward liquid velocity in a gas boot should be less than 0.5 feet per second, and it won't carry the gas bubble with it. And then that upward gas flow should be about 2 feet per second in the gas boot. Those are still pretty slow, but it'll give you a sizing criteria to build that gas boot. Filtration. Media filters are the most commonly used type. The media that's in these containers is sand, anthracite, which is what? It's coal. It's a type of hard coal, crushed up, or graphite ore. As you flow through those, you'll take out the big pieces in the filters. Pumps are going to be required to pump through those filters. You can't just gravity flow, because most of the time you're going to be introducing flow from the bottom. Or you will have to flow through the bottom. You're going to have pumps for some of the cycle. In the Civils Design book, we don't go into this in class, but there's a section on rapid rate sand filters. Their recommended design rate is about 2.5 gallons a minute per square foot of filter area. This is a cross-section of what a rapid rate filter would look like. Our raw water inlet would come in the top and go through a sand and gravel, and usually these are graduated filter materials, the finer particles here and then the heavier on bottom. And then the filtered water is taken out. But for that same filter, we got to have the backwash capabilities, and we go just the opposite way. We have our clean water tank hooked up to our filtering pump, come back in the backwash supply and out the top, and then we'd be draining the filter from the top. That sounds counterintuitive, but you got to pump through it and drain it back loosen those particles back up and get the trash out the top. And notice that source of that's the WHO, which is what? That's the World Health Organization. This is one of their drawings because these are the first stages in water treatment plants that are very, very economical and are used in a number of places in the world where they're treating water for drinking water. A lot of municipalities use this same principle. They just build big concrete structures and run their waters through similar filters. This is what a sand filter looks like. It's just looks like a small tank. Notice the big one down here. It's 12 feet by 5 feet tall, not very tall at all. And it will treat, based on their rate recommendations, about 9,400 barrels a day. I don't know how many of you are doing the water flood project, but when you size how many barrels a day, it's going to be a lot more than this. Think how many of these filters you're going to have. And this reminds me too that not all engineers think alike, because you don't always agree on things. I worked for a company that at one time we were buying lots of properties, and our favorite companies to buy from were from the big companies. So we could go in and make money coming behind them, fixing things that they hadn't done, and operate a little cheaper and make money on it. When we do that, we do what's called due diligence trips. We go around to the fields, look around, see what we were buying, and make sure we understood what we were getting into. We go in this one building, and it was as tall as this ceiling in here, and it's just like corrugated tin around it. And we walked in, and there's this huge filter sitting out here in this water flood out near Big Spring, Texas. Big filter sitting in there. Had new piping gone to it. This was an old water flood. The filter had never been used. And so the Midland office for that major oil company was a district office. And the regional office was back in Fort Worth. And the regional office decided they needed more filtration on the water. And the district office said, no, we don't. Regional office won, and so they bought the filter and sent it out there and said, hook it up. So the district office hooked it up and never turned it on. So, I mean, that's a true story, which it's hard to find in the oil field. That's a true story. But it tells you that engineers will have different opinions about things. Just because the guy's the boss and came from above, they did it. It seems strange, doesn't it, right? That could never happen. Happens. Injection pumps. We're not going to go back over all the criteria for designing pumps. There's been a couple of lectures, number 8 and 9 if you want to look them up, about centrifugal and PD pumps. But when we make our choice for the injection pump that we want to use for a water flood especially, we make it on 2 criteria. What's our capital cost and what's our operating cost? Because you can get high pressure centrifugals, you can get some relatively high volumes out of PD pumps. But we've got to look at which one is more efficient. If I had a pump to choose, one was a centrifugal and one was a PD pump, which one would be more efficient? The PD pump is more efficient. What if it costs more? Then I've got to look at what's the cost of electricity to run those, or other power that I put on that pump. These are PD pumps. This is a quintuplex. This is a triplex. A couple things about those pumps. They're heavy. They require big solid bases to set them on, because as the pump has the mass of the pump sitting there, as well as the forces that are created by that piston or that plunger going back and forth. And in this case, you've got 5. In this case, you've got 3. And so that plunger force gives you a vector in one direction. The weight gives you another vector. Where those vectors meet, there has to be a big base under there receiving that resultant force. look at all the parts. There's valves in the discharge side, there's valves in the suction side, there's plungers, there's connecting rods, there's a crank back here through this, there's probably a lube oil motor. There's lots of moving parts on a PD pump. But remember, it's more efficient. So what price do I pay for that? You've got to run those economics. This is a multi-stage centrifugal, and this is a station I designed after I'd been out of school about 4 years, and I'd never seen one of these. We had some, and this is down on the New Mexico border, down around Jow, between Jow and Orland. You got that? This is the centrifugal pump. Remember, like we saw at Oxy again, the pump is connected to the suction on a tank. It goes through a control valve for startup, because we always want to start a centrifugal pump against what kind of valve? Open or closed? Closed valve. If we started against an open valve, if we look at the curves on a centrifugal, it's going to go to the maximum horsepower and we burn up the motor, starting up on a high, on an open valve. So we start against a closed valve, and we put one in right there for that. Then we come down the line, it comes here, there is a recycle line. We may not need all the capacity we're going to put out of the pump, so we got a bypass line where we can go back to the tank with it. Schematically, it looks like this. There's our head tank. We come through the pump, meter it, and then here's our control valve to open up against. And then we can go from there out to the headers, to the field distribution, and we've got the ability with a second control valve to bypass back to the tanks if we need to. Notice the meter is between the pump and the control valve. What would happen if I put, and this was a turbine meter, let's say, if I put the meter on the other side of the control valve, what would happen? What kind of readings would I get? It'd probably be high. And why is that? Yeah, when I open that valve, I'm going to open it up, and if the meter's downstream of it, it's going to see that rush. And so I always want to put my meter where it doesn't see a separation pressure where gas can break out of it. We'll talk about that a little bit too. So our pumps have to be set on concrete pads, especially PD pumps with a mass 1.5 to 2 times greater than the pump weight, and how the mass is distributed is important. The pump metallurgy has to be selected to be corrosion resistant. Most of the time it'll be an aluminum bronze fluid end. You can build them out of stainless steel. A lot of frac pumps are made out of stainless steel just for that, plus the higher pressure rating. And then ceramic plungers are common. It doesn't have to be steel, but those are all corrosion resistant metals and materials that can be used in the fluid ends.